Good day. It's good to be with you once again. Today we're going to start talking about multiple integrals, specifically double integrals over rectangular regions. This is the beginning of a new topic, but it builds upon stuff we've done in the past with integration. And I got to say, the pictures are fun. Some of the questions are fun. It can be a little bit long and drawn out, especially by the end. But I think that this is a topic that will be a treat for you. Chances are when you're done with calculus 20 years down the road, one of the few things that you'll probably remember from the end of calculus is these double and later triple integrals, because the pictures are cool and the questions look kind of cool with all the symbols that are floating around in them. So you were in for a treat. Here we go. Double integrals over rectangular regions. So let's start with a review of the definition of integrals from earlier in calculus. So definition: an area A of the region S that lies under the graph of the non-negative continuous function f between A and B is the limit of the sum of the areas of the approximating rectangles. That is, the definite integral from A to B of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I star delta x, where n is the number of subintervals, closed intervals from xi minus 1 to xi of equal width delta x, and xi star is called the sample point and is any number in the subinterval xi minus 1 to xi. So this is an old concept to you, I hope. So we're trying to find this area under the curve. And to do that, we split things up into rectangles. Maybe like this one. The width of each rectangle is that delta xi. The left boundary is xi minus 1. The right boundary is xi. Right in the middle is our xi star. And so in order to approximate our area of our total area, we find the area of just the single special ith rectangle. And so that would be the function evaluated at xi star times the width, delta x. We add all these puppies up, then take the limit, allowing the number of rectangles to go to infinity, i.e. the width of the rectangles to go to 0, and we have our definition of the definite integral, our old friend from calculus 2. We are going to define the double integral in a similar manner. So definition of double integrals. In a similar manner, we consider a function f of two variables defined on a closed rectangle R from A to B by C to D. These should be lowercase c's and d's. Where this region would be the set of all xy's in R2 such that A is less than or equal to x is less than or equal to B, and C is less than or equal to y is less than or equal to D. So let's just make sure you're tracking what's going on. So our rectangle R is this region at the base in the picture, and the x values are going from A to B, and the y values are going from C to D. And we suppose that f of xy is greater than or equal to 0. That is, it's above the xy plane. So here's our f of xy. It's this surface here. Maybe I'll change colors on that. Let's call f, let's make it blue. And the blue is above the yellow rectangle. Let S be the solid that lies above R and under the graph of F. So it's this region here, and it's going to be a solid, right? Something like that. So it's like a solid prism, if you will, but in this case, it's kind of got a curvy top. So let S be the solid that lies above R and under the graph of F. That is, S is equal to the set of all x, y, z's in R3 such that 0 is less than or equal to z is less than or equal to f of x, y. That is, we're between the yellow and the here's the yellow and the blue. And the xy's are in R, which is the yellow region. Our goal is to find the volume of S. The first step is to divide that rectangle R, that was the yellow region, into subrectangles. We accomplish this by dividing the intervals from A to B into M subintervals, x of I minus 1 to xi of equal width, delta x, which is B minus A over M, and dividing the intervals CD into N subintervals, yj minus 1 to yj of equal width, delta y equal to D minus C over N. And so notice that we have a whole bunch of little subintervals in the x. And the one we care about here is this xith this xith rectangle. And then we also have a whole bunch of subintervals in the y direction. The one we care about is the jth one. Notice in this case, we're saying that M, the number of rectangles in the x direction, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in the picture, we have M equals 10. And in the picture, we have how many subintervals in the y direction? We have 1, 2, 3, 4, 7. In the picture, we have n equals 7. And in the picture, we're saying that our I would be 1, 2, 3, 4, 5, 6. It would be the sixth. This would be like the I equals 6 rectangle. And our J would be 1, 2, 3, 4. Our J would be 4 because we were in the sixth rectangle horizontally and the fourth vertically. Let's see. So that's our subdivision. Let's look at a manipulate so that we can get a clearer picture of what's happening here. So what I want to point out is that we have different regions that we're talking about. I could change the number of regions. Notice we're just kind of moving along through those regions. And those regions are all like directly below the surface, right? So we're looking for the volume of this solid that is above that rectangular region there. You could change your A's, which would be the back point in the A. You could change your B's, the front point in the X direction. Back point C is the back point in the Y's. D is the back point in the Y's. Okay, so pretty easy stuff. In the picture, notice that all of the sample points are all exactly in the middle of the rectangles, but they don't have to be. They can be randomly spaced at any point in those regions, which is the star point. So what we care about in this picture, and we care about in the other picture, is focusing in on just that Rij rectangle, and we care about the sample point that's in it. And notice those sample points could move around various points inside the rectangles. So by drawing lines parallel to the coordinate axes through the endpoints of these subintervals, not iteravals, there's a typo here. This is intervals. We form the subrectangles Rij equal to the region from xi minus 1 to xi by yj minus 1 to yj. So those are kind of the horizontal and the vertical starting and ending points. And each of these regions has an area delta x, which would be delta A, which is the delta x times the delta y of the rectangle. if we choose a sample point xij star comma yij star in each rij, that's in each little teeny rectangle, then we can approximate the part of S that lies above each rij by a thin rectangular column or box with base rij and height f of rij star comma y of ij star. The volume of this box is the height of the box times the area of the base rectangle. That would be f of ij star comma y of ij star times delta A. That's a lot of symbols, but it's actually not that difficult to see what's going on. What we're saying is we're building a rectangle. Here's our base. Down below, our base has an area here of delta x times delta y, which is the same thing as our delta A. And then it's got a height. So it's a, let's see if I can zoom in here for a second. So we've got a prism that we're creating here. And the height of the prism, that's the f of xij star comma y of ij star. Right, and it's that height is coming from whatever sample point we happen to choose. So it's a complicated looking statement, but pictorially it's not that difficult. Let's look at a manipulate, and I hope make this even easier to see. All right, so this is the same type of diagram as before, but now on top of each one of those little sub little mini boxes on the base, we have built this prism. And so you should be able to see the prisms kind of walk through the region. The heights, like see how the height of the prism or the column is determined by the sample point. So it's exactly above that sample point. See if you can see that. So it's exactly above the sample point below. To the surprise of no one, if we increase the number of divisions, you can sort of see where this is going. It looks like if we add all these puppies up, we're going to get a better and better approximation for the total volume that we're looking at. Again, the height of, or the volume of each one of these boxes is the area of the base, that's the delta A, and then times the height, which would be our f of xij star or comma yij star, or in this case, in this particular explanation, it's an xk star, yk star. But same exact concept as before. So surface is right above the rectangle, and we can split that rectangle up into little boxes and find the heights of the columns between the rectangle and the surface. If we follow this procedure for all the rectangles and add the volumes of the corresponding boxes, we get an approximation to the total volume of S. That is, the volume is approximately equal to the double sum from I equals 1 to m, and then j equals 1 to n of f of xij star, comma yij star, delta A. This double sum means that for each subrectangle, we evaluate f at the chosen point and multiply by the area of the subrectangle, and then we add the results. The expression sum from I equals 1 to m, the sum from j equals 1 to n of f of xi star, ij star, comma yij star times delta A is called a double Riemann sum and is used as an approximation to the value of the double integral. Notice how similar it is to the Riemann sum for a function of one variable. Let's look at a manipulate here. So here's that same surface, and what I simply want to point out is that as the number of boxes increases, this kind of boxy version of the volume looks better and better. Or if I even get rid of the surface, you can see that as the number of divisions increases, the whole surface starts to look smoother and smoother and smoother. Which I gotta say is pretty doggone rad. Now, we don't really want to be adding up a whole bunch of volumes of boxes, but this very much reminds us of what we've done earlier. And so it gives us hope that all this stuff is going to work just perfectly. Here, notice we're with 380 different boxes, and things look pretty smooth. And you could imagine if we let that number of boxes go to infinity, it would get even better. So our intuition tells us that the approximation given becomes better as m and n become large. So as we would expect, this would be typo here. So as we would expect, v is equal to, not approximately equal to, but equal to the limit as m and n go to infinity of the sum from I equals 1 to m, of the sum from j equals 1 to n, of f of xij star comma yij star times delta a. We use this expression to define the volume of the solid S that lies under the graph of the continuous non-negative function f and above the rectangle R. In the case where f has both positive and negative values on R, it represents a difference of two volumes. The volume of the solid that's above R but below f minus the volume of the solid that is below R but above f. We call this difference the net sign volume between R and f. Thus, a positive value means that there's more volume above R than below. A negative value means that there is more volume below than above. And a zero means that the two volumes are the same. Limits of this type occur frequently, but not just in finding volumes, but also in a variety of other situations as well, even when f is not a positive function. So we make the following definition. Definition. The double integral of f over the rectangle R is the double integral over the rectangle R of f of xy dA, and is equal to the limit as m and n go to infinity of the sum from I equals 1 to m, of the sum from j equals 1 to n, of f of xij star comma yij star times delta a, if this limit exists. A function f is called integrable if the limit above exists. It is shown in courses on advanced calculus that all continuous functions are integrable. Now that we've completed our theory, or at least talked through our theory, let's start working through some examples. So example 1, if R is equal to the rectangle from 0 to 4 by -1 to 2, and m equals 2 and n equals 3, we want to estimate the volume of the solid that lies between z equals 1 minus xy squared and R. In A, we're going to take the sample points to be the upper left corner of the rectangles. So what we're going to do is we're going to draw R. So I have my xy plane, and I notice that my R is going to go from 0 to 4. That would be 0 to 4, and from -1 to 2 would be -1 to 2. And so my rectangle will look like this. Okay, so this is my rectangle R. And then we're told that we want to have m equals 2, so that would be 2 subdivisions in the x. So we could divide this in half in the x. And we're told we want n to equal 3, so I'm going to have 3 subdivisions in the y. I have 1, 2, 3. So there's my 6 rectangles. And then we're told to take sample points in the upper left corner of the rectangles. So upper left corner, so that would be here, that would be that corner, and 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 that corner. Okay. Let's make sure we know what our values are. So notice this would be x equals 0, x equals 2, x equals 4, y equals -1, y equals 0, y equals 1, y equals 2. All right, and we also know that the area of each rectangle, the area of the rectangles, the little rectangles, equals the width, 4 minus 0 divided by 2, or 2, times 2 minus -1, 2 minus -1, which is 3 divided by 3, or 1. So our areas of each of these rectangles, our delta A, is equal to 2. So this is our delta A. So 3, we can add up, find the sum or write out the sum. So here we need to find the height at each of these points. So we're going to find, let's see, let's pick it doesn't really matter our order, but let's pick an order that might help us. So I go 1, 2, 3, 4, 5, 6. That's the order I'm going to write these in. So first I want to have f of this thing up here is our f of xy. So I'm going to have f of, it looks like 0, 0 times delta A, plus f of 0, 1 times delta A, plus f of 0, 2 times delta A, plus f of, so this is the first, the second, the third. Now I'm on the fourth, so it'll be f of 2, 0, 2, 0 times delta A, plus f of 2, 1 times delta A, plus f of 2, 2 times delta A. Oops, delta A. Okay, so we've written out that sum. Now we got to try to figure out what that thing is. Remember that z, or f of x, y, is equal to 1 minus xy squared. One minus xy squared. So let's see. So over here, we would have, it looks like there's a common factor of delta A in all of that. So we could, and our delta A is equal to 2. Remember this 2 delta is the same thing we have throughout. So maybe we'll put that out front. So this is going to be equal to 2 times, here's that delta A. And now we need f of 0, 0. So that'd be 1 minus 0, or 1. Let's get some color in here. So this one is going to be 1. Plus f of 0, 1. So when x is 0, so I think I'm still going to get a 1. So this one right here would also be 1. Plus now f of 0, 2. So 1 minus 0 times 4, still 1. Plus, now we're back to blue, f of 2, 0 would be 1 minus 2 times 0, or still 1. And this one's blue. Plus, now things get a little bit more exciting. So we get, for the green, f of 2, 1. So it'd be 1 minus 2 times 1, 1 minus 2, or minus 1. That one was green. Plus, let's see, that's an ugly plus, even for me. So then we have f of 2, 2. F of 2, 2 would be 1 minus 2 times 2 squared, 1 minus 2 times 4, 1 minus 8, or negative 7. Right? So all told, that tells us that we have, let's see, 1, 2, 3, 4, minus 1, 3, minus 7 would be minus 4 times 2, so I have minus 8. Okay, and so this minus 8 would represent the approximate, not the exact, but the approximate volume under, I put it in quotes because of the fact that our, I put it in quotes because of the fact that since it's negative, clearly our surface is mostly living underneath the XY plane. The approximate volume of the solid. In part B, we're going to do the same exact question, but now we're going to look at a different set of sample points. So once again, I'm going to start by drawing my rectangular region from 0 to 4 and from minus 1 to 2. So it looks like we're going here. But now my sample points are in the middle. The area of each region is going to be the same, but our volume here will be approximately equal to 2. That's the delta delta A. And then we're going to have all those midpoints. It looks like the x values are nice. So we'll have like f of 1 comma minus a half plus f of 1 comma positive a half plus f of 1 comma 3 halves plus f of 3 comma negative 1 half plus f of 3 comma positive a half plus f of 3 comma 3 halves, right? So those are the midpoints of each of these subrectangles. So now we got to figure out what those values are. So that would be, let's see, 2 times, I think we're not going to be quite as friendly as we were before. Remember, once again, that we have z equals 1 minus xy squared. So we're going to get a whole bunch of half squareds and negative half squareds, et cetera, et cetera. So I've got, pardon me, my screen sharing stopped. All right, so now we've got to evaluate our function. So we have 2, again, that 2 is our delta x, or delta A, I should say. And so here's that 2. And now we've got to evaluate this function in a whole bunch of different places. So first, we could go for the blue. And so our blue is going to be, we have 1, so negative 1 half squared would be positive a quarter. So I'm going to have 1 minus 1/4, which is 3/4. Plus, now we'll look at the green. So that would be, again, 1/2 squared would be 1/4. So 1 minus 1/4. So again, it's going to be 3/4. Plus, now we'll look at the purple. So 3/4 squared would be 9/4. So I'm going to have 1 minus 9/4 would be minus 5/4. Okay. So now we're back to a blue one. So if we have negative 1/2 squared, that will be 1/4. So 3 times 1/4. So 1 minus 3 times 1/4, or 1 minus 3/4 is 1/4. So that's going to be my blue. Plus, now we'll look at our green one. F of 3 comma 1/2. So 1/2 squared is 1/4. 3 times 1/4 is 3/4. 1 minus 3/4 is 1/4 once again. Plus, and then last but not least, we have f of 3 comma 3/2. So 3/2 squared, so it would be 9/4. 9/4 times 3 would be 27/4. 1 minus 27/4, 4/4 minus 27/4 be minus 23/4. And let's see, all of that, what does that add up to? So minus, I think this is, let's see, 3 plus 3 is 6, minus 5 is 1, plus 1 is 2, plus 1 is 3, plus negative 43 is negative 20 over 4. Negative 20 over 4 would be negative 5 times 2, so that would be negative 10. And so again, this negative 10 that we found here would be the approximate volume under the surface. Again, I say approximate volume, and also the under is kind of funny because most of this surface would be living underneath the XY plane. So that's why you have the negative number and the air quotes around that particular quantity. You can see this is kind of tedious and time consuming, but it's not actually that difficult. Here's the whole question all together. So key idea here. A double integral represents a quantity, say a volume, but it does not contain any inherent mechanism for calculating the quantity. For that, we need an iterated integral. Iterated integrals. Except in the simplest cases, it is impractical to obtain the value of a double integral from its limit definition. We now see how to evaluate double integrals by calculating two successive single integrals. The partial derivatives of a function f of xy are calculated by holding one of the variables fixed and differentiating with respect to the other variable. Let's consider the reverse of this process, partial integration. The symbols, the sum from a to b of f of xy dx and the sum from C to D of f of xy dy. Please note two variables here denote partial definite integrals. The first integral, called the partial definite integral with respect to x, is evaluated by holding y fixed and integrating with respect to x. Similarly, the second integral, called the partial definite integral with respect to y, is evaluated by holding x fixed and integrating with respect to y. Example 2. Let f of xy equal xy squared. Find the integral from 0 to 1 of f of xy dx and the integral from 2 to 3 of f of xy dy. So first, let's look at the integral from 0 to 1 of f of xy. That would be xy squared dx. So in this particular case, we have constants in our limits of integration, and we are integrating with respect to x, so we can treat our y squared as a constant. So if you will, you could think about taking that y squared out of the integral and just having the integral of y squared times the integral from 0 to 1 of x dx, which would be y squared times x squared over 2 from 0 to 1. Evaluate at 1, you're going to get a half. Evaluate at 0, you're going to get 0. And so this will be y squared over 2. Notice that partial integral with respect to x at the end will have, here I'm integrating with respect to x, and at the end there are no x's. No x's. So it's like we got rid of the x's. Similarly, if we looked at the integral from 2 to 3 of f of y squared, f of xy, which is xy squared dy, here we're treating y as our variable. So as far as this integral is concerned, x is a constant, so we can pull x out front. The antiderivative of y squared with respect to y would be y cubed over 3. And we're integrating from 2 to 3. When we evaluate at 3, we're going to get 27. When we evaluate at 2, we're going to get 8. And so 27 minus 8 is 19. So this will equal 19 over 3x. Here again, notice we integrated with respect to y, and in the end, there were no y's. It's like we integrated out all of the y's in the integrand. As we just said, a partial definite integral with respect to x is a function of y, and hence it can be integrated with respect to y. Similarly, a partial definite integral with respect to y is a function of x, which can be integrated with respect to x. This two-stage integration process is called iterated or repeated integration. And so let's see what's happening here. Notice when we take our integral with respect to y, we end with a function that has no y's in it, but still has x's in it. And so then we can integrate with respect to x. Similarly, if we have an integral with respect to x, after we've evaluated that definite integral, all the x's will be gone. We'll just be left with y's. And so it makes sense that we could then integrate with respect to y. Example 3, evaluate the following. And I just want to make it clear what's going on here. Notice that in A, we have y then x, and then in B, we have x then y. In A, the outer limit is -1 to 1, and the inner limit is 0 to 2. In B, the outer limit is 0 to 2. The inner limit is -1 to 1. So these are just sort of the same question, but in the reversed order. We want to see what happens here. So in A, we want to find the integral from -1 to 1 of the integral from 0 to 2 of 4 plus 9x squared y squared dy dx. So to do this, we will say this is the integral from -1 to 1, and then we're going to just focus on that inner part. And we're going to take the antiderivative of from 0 to 2 of 4 plus 9x squared y squared dy all dx. And so we're just going to focus on this partial integration. So it'll be the integral from -1 to 1 of, let's see. So if we're integrating with respect to y, the antiderivative of 4 would be 4y. We're integrating with respect to y, the antiderivative of 9x squared y squared would be 3x squared y cubed. And we're evaluating from 0 to 2, and that would be from y equals 0 to y equals 2. And all this is still dx. So when y equals 0, we're going to get 0 in both cases. When y equals 2, we will have 8 plus 2 cubed is 8, so 3 times 8 would be 24, so I'll have 24x squared dx. Now this is a Calc 1 question, so this would be 8x plus 8x cubed from -1. Ooh, I have -1 to 2 written up here. This should be a -1 to 1. Pardon me. -1 to 1, which would be, let's see, 8 plus 8 minus -8 minus 8. And that altogether looks to be about 32. And this 32 would represent the exact area under the surface. In this particular case, we don't really have any concerns about whether, like, what does under mean in this case, because of the fact that our surface is going to be entirely above the xy plane, because notice you have the x squared, y squared. So that's integrating in the first direction. Now let's do the same question, but integrate in the other order. So here we would have the integral from 0 to 2, and then I want to find the antiderivative with respect to x. So this will be 4x plus 3x cubed y squared from x equals -1 to x equals 1, and then we still have a dy that's hanging out at the end. So this would be the integral from 0 to 2 of, looks like we have 4 plus 3y squared minus 4 minus 3y squared dy. Let's combine like terms. So I think I've got 8 plus 6y squared dy. Antiderivative would be 8y plus 2y cubed from 0 to 2, which would be at 0, this is both are going to be 0. So it looks like we'll have 16 plus 2 times 8, or 16, which is once again 32. So I don't think it should be a surprise to you but in case it is, notice you're going to get the same exact area under the surface of 32, regardless of the order in which you do the integration. Let's look at a manipulate to try to understand what's going on with these iterated integrals graphically. So here we are integrating first with respect to x and then with respect to y. So when you do that, when you integrate first with respect to x, what you're doing is you're creating a function of y, this area function, and we're letting that area function sweep along the y-axis. We integrate with y with respect to y first, we create an area function with respect to x, and we let that area function sweep along the x-axis. But the key here is that either way, you're going to be sweeping out the same amount of volume. So it's an iterated integral, get the same thing either direction. It's no accident the two iterated integrals have the same value. Sometimes finding one is easier than finding the other. So let's evaluate the double integral over the rectangle R of x cosine xy dA, where R equals the integral or the region from 0 to pi in the x by 0 to pi over 2 in the y. And let's try to evaluate it in both orders, if that's possible. And actually, it might not be super possible. So let's see. So we start with that general double integral that doesn't have any built-in order in it. Here's our x cosine of xy dA. So there's no order there. And then we'll rewrite it as an iterated integral. So we don't really know which will be better. So maybe I'll write it as 0 to pi over 2. And we have x cosine of xy d pi over 2's. So notice that these guys are here. So we're going to go with respect to y first. And then we'll go dx because the 0 to pi here is in the x variable. Okay. So if we want to find the antiderivative with respect to y, this will be the integral from 0 to pi of, let's see, antiderivative of this was, remember, x is a constant as far as this integral is concerned. So you could sort of picture it coming out front, although we don't have to write this. Antiderivative of cosine would be sine. So let's see what happens if we get sine of xy. So if I took the derivative of this, derivative of sine would be cosine xy times the partial derivative of xy with respect to y would just be x. Yep, I got back what I started. So 0 to pi over 2 dx. If we put in, and these are, notice y's. So y equals 0, y equals pi over 2. So if I put in y equals 0, sine of 0 is 0. So we'll just have sine of pi over 2 x dx. I think maybe I'll change my question here. Let's go from, instead of going 0 to pi, let's go 0 to 1. Just make the numbers a little bit easier to work with. So then the antiderivative of sine of pi over 2x would be a negative cosine of pi over 2x. But then I also need to multiply by, looks like a 2 over pi to get rid of that coefficient from the chain rule. And we're going to evaluate from 0 to 1. And so this will be, let's see, minus 2 over pi times the cosine of pi over 2 minus the cosine of 0. Cosine of pi over 2 would be, that's the x value, pi over 2, that would be 0. This would be 1. And so all told, we would have minus 2 over pi times minus 1, or just 2 over pi. So that's if we integrate with respect to x first, or sorry, y first and then x. So let's try it in the other order and see what happens. So in the other order, we would have the double integral across the rectangle R of x cosine xy dA. And we could write this as the iterated integral. So it'd be the integral. Now it's going to go 0 to 1 on the inside, 0 to pi over 2 on the outside of x cosine xy. And here we're going to go dx dy. Golly. Let's see what happens here. So now we need to integrate this inside bit. So this will be the integral 0 to pi over 2. And then I need to find the antiderivative of x cosine xy. I think that's going to require integration by parts, which it's been a while for me. So integration by parts. So I have my u and my dv. So my u will be x. My dv will be cosine xy dx. So my du will be dx. My v will be sine of xy. Let's see. So if I take the derivative of this with respect to x, there'd be a y that would come out, so I better divide by y here. Something like that. So all this garbage is going to be uv, so I'm going to have x over y times the sine of xy minus the integral of v du, which would be sine of xy over y du, which is a dx. Okay, so that's my antiderivative. I'm going from 0 to 1, and there's still a dy outside. We could keep going. The y in the denominator here looks a little bit scary, but it's actually not that scary because remember our variable is x, and so it's not going to be too bad. Let's see. But it's definitely a lot worse. So we could keep going. And maybe I'll just say, no, let's stop. Let's stop. And why are we going to stop? Because the point of this example, because I think it's kind of easy to lose track, is the point of this example is that sometimes finding one of the integral in one order is better than the other. So in this particular case, this first one was pretty easy. And the second one was pretty hard. Could it work? Yeah, it could work if we're willing to work hard enough at it. But the point isn't to prove how good we are at integrals. The point of this particular example was to say, if you're given a choice, recognize that sometimes one order of integration is substantially easier than the other order of integration. Iterated integrals have an inbuilt order of calculation from inter-integral to outer integral. Fubini's theorem provides the basis for changing this order. So Fubini's theorem, if f is continuous on the rectangle R, which is in the x a to b and in the y c to d, then the double integral over the rectangle R of f of x, y, dA is equal to the iterated integral from c to d, inner integral a to b of f of x, y, first with respect to x and then with respect to y. It's also equal to the double integral from a to b and c to d, f of x, y, dy, dx. So notice here we have the x's on the inside, here we have the x's on the outside. In this, or we have the y's on the outside and the y's on the inside. So you can swap the order to do it in whichever way is convenient. Again, over here you have a double integral. Double integral does not include kind of like a built-in computation method. Over here on the right, you have those iterated integrals. More generally, this idea that you can reverse the order is true if we assume that f is bounded on R, f is discontinuous, there's a typo here, only on a finite number of smooth curves, and that the iterated integrals exist. Example 5. Use a double integral to find the volume of the solid that is bounded above by the plane z equals 4 minus x minus y, and below by the rectangle R, which is the set of all x, y's, where 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to 2. So we're saying we want to find the double integral across R of 4 minus x minus y dA, and we could write this as an iterated integral. We can choose our order. As we learned earlier, it might be easier one way or the other, but we don't know that yet. 4 minus x minus y. And in this case, I'm going 0 to 1, or dx is my inner, because the 0 to 1s match with the x's. And then dy, because the 0 to 2 matches with the y's. So this would be the integral from 0 to 2 of, here we're anti-differentiating with respect to x. So we'll have 4x minus x squared over 2 minus yx on 0 to 1, and there's still a dy. Notice this is x equal to 0, x equal to 1. So when we put in 0, you're going to get 0 in all those cases. That's easy. So now the integral from 0 to 2 of 4 minus 1/2 minus, when x equals 1, you'll just have y dy, which would be 4 minus 1/2 would be 7/2. So this will be 7/2 y minus y squared over 2 on the interval 0 to 2. At 0, once again, both these terms will be 0. At 2, I would have 14/2 minus 4/2, or 10/2. So 14 minus 4 is 10/2, or 5. And this 5 would represent the exact area, or exact, not area, but volume, underneath the plane, but above the xy plane. Here is the full solution to that question. I want to teach you a little handy trick, and this is a handy trick. Ooh, I should probably change my lettering here. Handy trick when f can be written as a product of a function of x and a function of y. Maybe I will change this to a big F. So big F of xy can be written as little f of x times g of y, and it's integrated over this rectangular region. So then in that case, you can say if you have a product on the inside where the yellow f of x is only a function of x and the blue g of y is only a function of y, and we're over a rectangular region, then we can write this as an integral of the yellow f of x function times a separate integral of the blue g of y function. That is, you don't have to do the iterated, like do one and then do the other. You can sort of do both of these integrals at the same time. It's a handy trick. It'll save you some time, and it's a great trick to have when your integrands are simple. Example 6, evaluate the double integral over the rectangular region. My integrand is 5y cubed cosine x dA, and my rectangular region is R equal to the set of all x, y's, where x is between 0 and pi over 2, and y is between 0 and 1. So notice here we have our f of x is cosine x, and our g of y is 5y cubed. So I have a product of a blue times yellow, or function of y times function of x. I also notice that we have that rectangular region R. That's important. And so we can split this thing up. So this will be equal to the integral of cosine x, and my x's are going from 0 to pi over 2, dx, times the integral from 0 to 1 of 5y cubed dy. Notice no iterated integral required. And so this will be sine x from 0 to pi over 2 times 5 over 4 y to the 4th on 0 to 1, which would be, looks like 1 for the first one, and 5 over 4 on the second one, or just 5 over 4. Putting it in color, here's that cosine x, here's the 5y cubed, so where we split it up. And so there's the two, we took one double integral and we wrote one double integral as the product of two single integrals. No iterated integration required. Kind of nice and cool. Historical note. Fubini's theorem is named after Guido Fubini. Fubini was born in 1879 and lived most of his life in Italy. He worked in a wide variety of fields related to mathematical analysis, that's calculus and topics based upon calculus. During World War I, he shifted his work towards more applied topics, such as studying the accuracy of artillery fire. After the war, he studied electrical circuits and acoustics. Then in 1938, as he was nearing retirement, the fascists, led by Mussolini, adopted the anti-Jewish policies of the Nazis, led by Adolf Hitler. As a Jew, Fubini feared for the safety of his family, and so accepted an invitation by Princeton to teach there. So he came to America, taught here for a few years, and died 4 years later. And it's interesting that obviously many people, millions and millions died in the Holocaust, but there was also a huge influx of science talent into America, because we basically said, hey, if you are really good at your field, you can come to America and be safe. And so there are many mathematicians, in addition to Fubini, that sort of took this offer, and specifically, I think, ended up at Princeton. I think Einstein was in that group, Gödel was in that group, quite a few others. So there's your historical note, tying really World War II and the Holocaust to Calculus 3, which is pretty tight. Last little topic, the average value. So previously in calculus, we saw that the average value of a function of one variable on an interval from a to b is the average value of the function equal to 1 over the width of the function b minus a times the integral from a to b of f of x dx. So it was like the area under the curve divided by the width of the interval, and that gave us our average value of the function. Here we can define the average value of a function of two variables on a rectangle R similarly. And there's a missing A on a rectangle R similarly. So here we would say the average value of our function, which I wanted to highlight and not black out. The average value of our function would be equal to the 1 over the area of the region times the double integral over the region R of f of x y dA. If our function happens to be non-negative, that is f of x y is greater than or equal to 0, we can write this as the area of the region times the average value of the function is equal to the double integral over the region of f of x y dA. And this says that the box with base R and height, this is the average value of the function, has the same volume as the solid that lies under the graph of f. Last example, example 7. Find the average value of f of xy equal to tangent of x over square root of 1 minus y squared over the rectangle 0 to pi over 3 in the x and 0 to 1/2 in the y. So if we want to find f average, it's going to be 1 over the area of the rectangle times the double integral, and it's double integral over R of that thing, tan x over square root 1 minus y squared dA. Let's see if we can figure out what the R is. So our area of R would be area of R. So it looks like that would be pi over 3 times 1/2 or pi over 6. Okay, so that part's pretty easy. And now we want to set up our iterated integral. I don't know about you, but I'm a little bit nervous about the root of the 1 minus y squared bit. So maybe we'll take that on first and hope for the best. So this will equal 1 over pi over 6, which is the same as 6 over pi times the double integral of, I also notice I can use handy trick here. So we can use handy trick because this would be the tangent of x dx, the integral of 1 over square root 1 minus y squared dy. The x's are going from 0 to pi over 3, and the y's are going from 0 to 1/2. Golly, you might it might have been a minute since you integrated tangent, so we'll have to sort of play with these individually. So here we think about tangent as being sine over cosine. And if you think about it as sine over cosine, then we could let u equal cosine. U equal cosine, du would be negative sine x dx. And so we're going to end up with an ln showing up there. On the right side, I think this is an arc sine, if I remember. So I'm going to have, I think this is arc sine of y on 0 to 1/2. And this is one of those places where I always love the Google. We can just quickly take advantage of our of the Google to do our antiderivatives. Let's see. How about this? It's a new window. So I'm going to try Wolfram Alpha, my favorite site, and I could find the derivative, come on, of, and specifically we want to find of tangent x. So this is going to be minus log of cosine x. And one thing you'd have to know here is that for the for Wolfram alpha, log is the same as the natural logarithm. So this is not log base 10. This is our ln. So we're going to have a minus ln of cosine x. And then we also want to know the antiderivative of 1 over the square root of 1 minus y squared. And I think this is arc sine. Let's see if I'm right. Sure enough, it's the arc sine. So we took advantage of our tools to find our quick antiderivatives. And so it looks like we're going to have 6 over pi times, what is it, minus the ln of cosine of x. This one should be in brackets. From 0 to pi over 3 times the arc sine of 1/2. You think sine of pi over 6 is 1/2. So this would be pi over 6 minus the sine of 0 is 0. So there'll be a 0. Okay. And then the cosine of, so this is going to be, notice there's a pi over 6 here and a 6 over pi there. So those are together going to give you a 1. And so then we have minus the ln of cosine of pi over 3. Cosine of pi over 3 would be 1/2. The ln of 1/2 minus the ln of the cosine of 0 is 1. So let's see. Cosine of 1 is 0 minus the ln of 1/2 would be the same as positive the ln of 2. So all this stuff is just ln of 2. So this tells me, hence, f average is the ln of 2. So this would be the average height of that surface in this region. Here is the overall solution. So there you have this little lesson introducing double integrals. As you can see, there's kind of some fun stuff. There's some things to keep track of. The integrations will be not terribly difficult because the point is to learn about double integrals, not to learn about integration itself. You've done that previously. Honestly, if the integrals look really difficult, then I would encourage you either to think about switching the order of the integration in the iterated integrals, and or take advantage of your technology to finding antiderivatives. But there you have it. Another wonderful lesson on calculus. Take care, and I'll see you next time.